Hello, AP Chemistry students. I know that you're just as anxious to start spring break as I am, but we'll finish up a couple of these notes today so that we don't get farther behind than we are. We're moving into Chapter 19, and you can get out your study guide here. It's Entropy and Free Energy. And a lot of this will look familiar to you. So, either it will look familiar to you from things that we have done this year and some things that you've seen from your first year in chemistry. So we'll review first of all actually some physics concepts when we're talking about the first and second law of thermodynamics. The first law of thermodynamics, as it says here, states that the total energy in a closed system is constant. Now, this is where we've talked about this already this year in endothermic and exothermic reactions. The first one here, as an endothermic reaction, we can start making an enthalpy diagram. I'll put my enthalpy here. Time is on the x-axis here. We start with the reactants, and of course if it's an endothermic reaction, the products will end up with more energy than the reactants. We will put a little bit of, you remember what that's called, the height of the hill, right, activation energy to get the reaction to go. But here's what we mean, the application of the first law of thermodynamics. My delta H for an endothermic reaction is positive, and what happens is the exchange of energy here goes from the surroundings into the system. And we will be referring to the surroundings and the system. And the system is generally our chemical reaction, and the surroundings is how that reaction affects the area around it. So there's your exchange of energy. Energy does not come from nowhere. It comes from the surroundings into the system. We haven't defined enthalpy in a while, but our variable is H. It's defined as total internal energy. Again, a little review for you. And how do you find delta H, or how do you calculate delta H? Yeah, it's the summation of the heat of the products minus the summation of the heat of the reactants. For an exothermic reaction, of course, we again can start with our reactants. Exothermic, the products will have less energy stored in them than the reactants. Where did it go? Yeah, delta H goes, well, the energy goes into the surroundings. So in an exothermic reaction, that's why you feel the heat, because it's being dissipated from the reaction. Delta H is negative, and there is, go on down there, our activation energy. Do you remember some other ways to calculate delta H? Yeah, you can use Hess's law of heat summation. This one we haven't used in a while. Summation of dBB plus the summation of dBF. You remember what those stand for? It's the dissociation energy of the bonds broken plus the dissociation energy of the bonds formed. And the bonds being broken, it always takes energy. You have to put energy in to break a bond. So those are positive. When bonds are formed, energy is always released. So those values are negative. But again, note the distinction between the positive or the plus sign between the two because of the signs that are given to the bonds formed and bonds broken. All right. As we move up to spontaneous reactions. And it's neat to think, I think, of the idea of something being spontaneous. What does that exactly mean? When we apply it to occurrences in nature or chemical reactions, it's something that occurs without outside intervention. So occurs, without we accidentally got cut off here. A spontaneous reaction occurs without outside intervention. And I'll give you a couple examples of something that we consider to be spontaneous. For example, a ball. A ball will roll down a hill, but it will not roll up a hill, at least not spontaneously. We would have to apply some outside intervention in order to get it to do that, to roll up the hill. An ice cube. If I set an ice cube out on the counter here, it will spontaneously melt. We will not need any outside intervention in order for it to do that. If I were to spray a gas into this room, even a perfume, so that you could smell it, it would spontaneously fill the room. And then heat. Good old heat will flow from hot to cold, and not spontaneously vice versa from cold to hot. So we are going to be talking about driving forces in nature. You know, what would make a reaction occur spontaneously? And the first driving force in nature is an increase in entropy. The second driving force in nature, if you want to flip to the second page, is a decrease in energy. So we'll talk about those two driving forces in nature. And I have already defined an increase in entropy, or really defined what entropy is. It is a measure of disorder or randomness in a system. So the larger the disorder, the more entropy that a system has. The variable or the letter that we use to designate entropy is a capital S. And just to give you an example of what we mean by a measure of disorder or randomness, the entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas. And when you go back to the disorder, a solid, very rigid, you know, the particles still vibrate, still have some motion to them, but they are in the crystal structure. They don't have the freedom to move around, so they don't have very much randomness, at least compared to a liquid, where the particles still very close to each other, but they're not in the crystal structure. They have the freedom of movement to slip around between each other. And then, of course, in a gas, you have pew, pew, pew. They are able to move very randomly. They have a lot of space between them. It can move and they have a very large entropy. Oh, now we get to play a game. It's called Which Has the Greater Positional Entropy? Solid water or gaseous water? Positional energy. And I'm talking about the position of the molecules themselves. What do you think? Yep, you're right. It would be the gaseous H2O. How about oxygen under 1 atm of pressure or oxygen under 0.01 atm of pressure? Which one has the greater entropy? Yeah, it will be able to move a lot with greater randomness if it is under 0.01 atm of pressure. Alrighty, now we're going to apply them to actual chemical reactions and some phase changes here. And each of the following processes indicate if entropy is greater for the products or reactants and indicate the sign of entropy in each process. So we haven't done that just yet. We have CO2 going from a gas to dry ice. So we're going from the gaseous form to the solid form. Entropy is greater in the reactants. Oops, there it is. Delta S, the change in entropy, then for this particular system as it goes to a solid is negative as the entropy decreases. Here is entropy. We're starting with a solid, and you see these two ions here. They're actually just dissolving some potassium chloride in water, in a water solution. You want to think about positional energy. Where do the particles have greater freedom of movement? In the solid form or in the solution form? Yeah, it would be in the solution form. So it would be in the products, if we can call these products here. So in this case, your entropy is increasing. Now we have magnesium carbonate that we are going to heat up, and we're forming, you notice here we have a solid, and here we have a solid, but the solid is accompanied in the products by a gas. There's two reasons here why our products actually have greater entropy. And one of them is, well, you do have a gaseous product that's formed. The other reason is, if you look at the moles of particles or molecules, you only have 1 mole of substances in the products. You have in the reactants, sorry, you have 2 moles of products being formed. Because you have more moles of substances, you have more particles formed, so you would have more freedom of movement or more randomness. So delta S, in this case, is also going to be positive. Okay, so you can look at the state of the substance. You also may need to look at the number of particles that are formed. All right, now I am going to skip over to, all right, okay, we're going to do some calculations for delta S now that you have the actual concept down. So again, go to page 3 of your study guide, and we're going to talk about the third law of thermodynamics when we do the calculations for delta S. Have your stapled sheet that has the thermodynamic values on it handy. It has delta H, it has delta G, delta S, all of those values for you. It's your new best friend for the rest of this chapter. Calculating delta S is not going to be difficult for you because it's basically the same way that we calculated delta H. And if you remember when we talked about delta H, we had to have a standard to go by. We said that all elements in their natural state were assumed to have an enthalpy of 0. And then we could use those as a standard to determine how the compounds deviated from the actual elements. For the concept of entropy, we are going to assume that the entropy of a perfect crystal at 0 degrees Kelvin is 0. So that's the standard by which we were going to measure the entropy and the randomness of everything else. So we start with this assumption, first of all, that we can get a substance at absolute 0. When we do get it to absolute 0, it's going to form what we call a perfect crystal, whatever that is, and that it has an entropy of 0. The more complicated the molecule, the higher its entropy. And it is a state function. And if you remember how we define a state function, it means that there may be several different ways to calculate it or several paths of getting the actual value of the concept, but it doesn't matter how you get there, the value is still the same. So again, if you compare it to maybe going up a stairway, you start at the bottom of the stairs, you get to the top. that is a state function. It doesn't matter how you get there. If you go up 2 steps at a time or 1 step at a time, or you go up backwards, the end result is still the same. So there's our state function. Delta S of a reaction, and again you have that little degree mark, which means under standard conditions, and delta S of a reaction is equal to, we're missing a couple symbols here. This should be, whoops, that's supposed to be a summation symbol, of the number of moles of products minus, that's a minus sign, the summation of the number of moles of the reactants and their entropy. So again, the formula will look very, very simple, or similar to you as we calculated delta H. The first one we have here is N2O4 gas going to 2NO2 gas. And first of all, why don't we do a little prediction as to what might happen to delta S? We have 1 molecule of N2O4. It's going to 2 molecules of NO2. Would you expect that the entropy increases or decreases? Yeah, because we actually have more molecules, the same number of atoms, of course, but more molecules, the entropy should actually increase. Let's look up the values for this particular reaction, and we generally call reactions system. So delta S of this system is equal to, we'll put the brackets in, you have 2 moles of NO2, so 2 moles, and if you look at your chart, the entropy of NO2 should be 240.1. The units, joules, there's your energy units, per mole Kelvin. All right, those are our products, and then minus, we have the summation of, we just have 1 mole of N2O4. If you look up its value, it should be 304.8, and again, that's joules per mole Kelvin. So this overall value comes out to be, aha, just as you predicted, positive 175.8 joules per mole Kelvin. All right, so again, it's a new concept being delta S, but it's calculated very much the same as delta H. The next one here, we have Fe2O3. It's a solid combining with 2 aluminums, solid there also. And then we're getting 2 moles of iron and 1 mole of aluminum. Again, both solids. Ooh, do you remember what this reaction is by any chance? Yeah, this is a good old thermite reaction. So we are producing a lot of heat, at least in this. But when you look at the entropy change, you have 3 moles of reactants, you have 3 moles of products, you have basically the same states of matter here. You've got solid, 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 solid. So what should be our change in entropy? I don't know. Let's see. Delta S of this system is going to be, again, it's products, summation of the products minus the summation of the reactants. So my products here with the iron, if you look it up, there's 2 moles of iron. That's supposed to be a 2. And it is 27.78 joules per mole Kelvin. Plus, there's only 1 mole of the aluminum oxide here, and that should be 50.92 joules per mole Kelvin. All right, and minus, we have 87.40 joules per mole Kelvin for the iron oxide, plus 2 times the aluminum 28.3 joules per mole Kelvin. And again, notice, you were used to with delta H, the elements like the aluminum and the iron in their natural state, delta H is 0. But in enthalpy, we are comparing them to a perfect crystal, and their values are generally a positive enthalpy. Now, when we work this out, we get negative 37.5. That again is joules per mole Kelvin. Now, we talked about the fact that you have basically the same amount of elements, you have the same states, or you have the same amount of molecules. If you look at this, this is very close to being a zero change in enthalpy. It's a little bit of a decrease, but not a whole lot. All right. That is about all that I'm going to do with you today. You have enough to get you started a little bit on the worksheet that goes with this, at least doing some of the tedious problems with calculating delta H and doing the products minus the reactants. You have your notes to do over the chapter. So I wish you all a very good and safe spring break, and we'll see you for the final push in April.